the first application that I want to look at is the volume charge. So we have a solid here. This has a radius of A and has a volume. So this has a uniform volume charge density that's given by this quantity right there. Then I want to calculate the magnitude of the electric field at the point outside the sphere. So what are we talking about? We have, so this is a sphere, it has positive charges in it. So this is a volume charge. I don't know the number of charges that are inside, but what I know is that I know this value here. So rho is the total charge divided by the volume, which is 4/3 by A to the power of 3. Now, because I want to calculate the electric field at the point that is outside, then I can use this as my surface. And I simply look at all the electric flux that is coming out of this. So you can see that because this surface here, within this surface here, I have all the charge Q. So it means that when I calculate the electric field, right, it's just going to be equals to this quantity here. So the flux is E times the surface area. Is equals to Q over E naught. So when I'm calculating the value outside, I get this equation here. So you just verify this quantity. Now, if I'm inside, you're going to see that, so for example, if this is my new Gaussian surface here, then the question is that, how much amount of charge do I have in here? Again, you have electric field lines coming out. So the number of charges that I have in here, I can calculate it using this equation here. So this is just going to be some fraction. So this is some fraction of the total charge, which, again, if you substitute this quantity here, so the Q in that we've calculated here, taking a substitute here, you get this value of the electric field. So let me try to, I want to go over this again because I think here so I can really explain this. All right, so suppose I have a sphere, right? Remember that the basic definition that I'm going to be using is this equation. So so this is my main equation here. So what I want to show you here is a much more simple solution. So this is equals to Q inside. That's my main equation. Now, I have a sphere And this sphere has charges inside. Now, if you think about it, the electric flux, you can just write it as electric field times the surface area. So solving this equation, you get your electric field is always going to be equal to Q in divided by now let's also write this as KE. Let's write this as KE Q in over R squared. Where in this equation here, I'm saying that K in is this quantity here, 1 over 4. So this is the basic equation that we use all the times. Now let's see how we can apply this equation. Now, if we have a sphere and this is the radius of the sphere A, and I want to calculate the electric field at the point that is outside. So if I want to calculate the electric field at the point outside, this is what I'm going to use as my Gaussian surface. So this is my surface here. Now, so I'm going to look at the total flux through this. So notice that this surface here, for this particular surface, Q in is equal to Q, because all the total charge is in there. And so it means that when I'm calculating the electric field with the radius at a point, so I'm calculating the electric field at some point where, so when R is greater than A, so if I'm outside, then Q in is equal to Q. And so it means that my electric field is equal to Q in. So the electric field outside is very easy to calculate. Because outside, all the charge is inside that volume, right? So all what I just need to do is to say that Q in is equal to big Q, and then I get the electric field outside. And this equation is an equation that we've seen before. This is just the electric field of a point charge. Now let's see what happens if you want to calculate the electric field at the point that is inside. So again, this is the volume that we had. Now, if I want to calculate the electric field at the point R such that R is less than the radius A. So again, this is A, that's the radius. Now, this is my new point. So I want to calculate it at the point where it's inside. So this is R. So notice that in this case, R is less than A. So I need to look at how much electric field goes through that green surface there. So I just need to calculate Q in. So how do I calculate the charge that is within this? So Q in is the total charge that I have inside that smaller volume. Now I can calculate this by using this equation. I can say this is equal to 4/3. I don't know if this makes sense or not, but what I'm saying is that if I have a smaller volume, then the total amount of charge in this smaller volume is just a fraction, right? So take the smaller volume divided by the total volume, that tells me what fraction of charge that I have in there. Now let's see if this makes sense or not. If I look at this equation, if I were to put in R equals to A here, what do you think happens? If R equals to A, the volume is going to cancel, and then you just get Q in is equals to big Q, right? But because R is less than A, it means that Q in is going to be less than big Q. Now, so if you do the math here, everything cancels. This 4/3 cancels with this 4/3. Pi cancels with pi. And so you just end up with a value of Q in. So your Q in is just going to be equal to R to the power of 3 divided by A to the power of 3 times Q. Now, it means that if I'm outside, this is my new value for Q in. And so if I take that value and substitute it in here, I get the electric field outside is equals to KE. Now Q in is what? It's R to the power 3 over A to the power 3 times big Q, and then all of that divided by R squared. Now notice that if you divide this correctly, you end up with something that looks like this, KE Q R to the power 3. So that's the electric field if I'm outside. If I'm inside, this is inside. This is the electric field.